In the last lecture, we have defined vector space. Now we'll see the definition of subspaces. So we'll define like this. So let S be a non-empty subset of a vector space. Subset of a vector space V defined over field F. Symbolically, we can write like this: S is a subset of V. If S is also a vector space over F using the same addition and scalar multiplication operations, then S is said to be a subspace of V. It is not necessary to check all 10 of the defining conditions in order to determine if a subset is also a subspace. Only the closure conditions, that is A1 and M1, need to be considered. So we can say like this, that on non-empty subset S of a vector space V, vector space V is a subspace. So let us reiterate once again. So we say formally that a non-empty subset, remember, like we are saying, this is a non-empty subset S of a vector space V. When do we call it as a subspace? We call it as a subspace of V if and only if it satisfies the closure property under vector addition and scalar multiplication. That is, if we have two vectors x and y that is belonging to this subset S. Now we are writing in terms of this subset S, non-empty subset S, which then it should follow that this vector addition should also belonging to the subset S. And second, it should also satisfy this property for every vector belonging to this subset S. There should exist one scalar which is defined over field F, such that the multiplication of scalar times the vector should belong to this subset S. Only after satisfying these two operations or the properties, only after satisfying these two properties, we can say that S is a subspace of a vector space V. Or we can write this: it is a subspace of vector space V. Okay. So one can argue if S is a subset of V, where we know that this V is already defined as a vector space, then this set S inherits all the vector space properties of V except A1 A4, A5 and M1. However, in order to make it more clear, we will write here what those mean. A1 we checked for x, y belonging to set V, the vector addition should also lie within the set V. Then only we can say that V is a vector space. It is one of the key criteria we define as the set V is a vector space. In A4, we have seen that for x belonging to the set V, there exists an element 0 that is also belonging to vector space V, such that upon addition of these two vectors we will get back the same x vector that is further belonging to set V. And A5, for every vector x belonging to V, there exists a element minus x that is also belonging to the set V, such that the addition of these two will yield 0 vector. And M1 we have defined saying that the scalar quantity alpha is defined like it's belonging to certain field, and the vector is belonging to a set V. Then if we consider the scalar multiplication of alpha times vector, then it should be belonging to the set V. This was the property, closure property for scalar multiplication. So why we wrote all this is to focus on the particular notion saying that S, the subset of the vector space that is we have defined as S, will inherit all the vector space properties except these 4, A1, A4, A5 and M1. Why we are saying this statement is because see, A1, let me change the color, A1 together with M1 is nothing but A4 and A5. Take to observe, to prove this, observe that M1, here M1 property implies that minus x vector, we can write it like this, minus 1 times x, which is belonging to S for all x belonging to S, so that A5 holds. Since x and minus n both, now since x and minus x are both in S, this is also an x, this is also an S, we ensure that the addition of these two vectors will also belong to the set, and thus 0 is belonging to the set S. So it is only legible if we consider to check whether a subset of the vector space V is a, when do we call it as a subspace, if only and only if it satisfies these two these two properties A1 and M1.